Venus is a beautiful world hiding a terrifying secret. It is our closest planetary neighbor, often called Earth's sister, but this is a twin that took a catastrophically wrong turn. Beneath those serene, sun-reflecting clouds lies a landscape of unimaginable heat, pressure that would crush a submarine, and rains of corrosive acid. Yet this hellscape is not just a simple cautionary tale. It is a planet packed with profound mysteries that defy our basic understanding of how rocky worlds evolve. By the end of this journey, you will see our solar system in an entirely new light. We will uncover why its atmosphere whips around faster than the planet spins, investigate signs of possible volcanic eruptions happening right now, and even question if life could be hiding in its toxic clouds. Each puzzle is a piece of a cosmic detective story, challenging everything we think we know. What does the extreme fate of our sister planet make you wonder about our own world's future? This transformation begins with a deceptively simple process we know all too well: the greenhouse effect. On Earth, it is a delicate and necessary blanket. Sunlight passes through our atmosphere, warms the surface, and that heat radiates back as infrared energy. Certain gases like carbon dioxide and water vapor trap some of that outgoing energy, keeping our planet comfortably warm enough for oceans and life. It is a balanced system, but on Venus, this same process spiraled into an unstoppable, self-feeding catastrophe. The planet's atmosphere is now a crushing blanket of carbon dioxide, over 90 times thicker than Earth's air. This immense shroud traps heat with terrifying efficiency, creating surface temperatures hot enough to melt lead, around 860 degrees Fahrenheit. So what went so horribly wrong? How did a world that might have once been so familiar become a furnace? Scientists point to a few possible triggers. One leading idea involves water. Early Venus may have had vast oceans just like Earth, but being slightly closer to the Sun, those oceans may have begun to evaporate more readily. Water vapor is a powerful greenhouse gas. More vapor meant more trapped heat, which evaporated more water in a vicious cycle that eventually boiled the oceans dry. Without liquid water to absorb carbon dioxide from the air through processes like rock weathering, the gas built up relentlessly. Another theory points to colossal, planet-wide volcanic eruptions. Imagine eruptions so vast and prolonged they flooded the atmosphere with greenhouse gases from the planet's interior, overwhelming any natural balance. It is also possible Venus was simply born a little too close to the Sun's warmth to ever stabilize a temperate climate. This leads us to the concept of the Goldilocks zone, the narrow orbital region around a star where conditions are just right for liquid water to exist on a planet's surface. Earth sits perfectly within this zone. Venus, it seems, sits just on the inner edge, a location that may have made it uniquely vulnerable to a climatic tipping point. The story of Venus is not just an ancient history lesson. It is the most extreme example in our solar system of a runaway greenhouse effect, a stark and sobering warning of what can happen when a planet's climate balancing mechanisms fail. It forces us to ask a profound question about our own world, nestled safely in the habitable zone. Could a similar process, however slowly, ever begin here? This runaway heat is just the opening chapter of Venus's defiance. The planet holds another, equally baffling secret in its howling skies. While the scorching surface below barely moves, taking 243 Earth days to complete a single, sluggish rotation, the upper atmosphere above it is caught in a perpetual hurricane. It screams around the entire planet in just 4 Earth days, a phenomenon called superrotation. To grasp how alien this is, picture Earth. Our planet spins rapidly, completing a full turn every 24 hours, and that spin drags our weather systems along with it, creating the predictable trade winds and jet streams. Venus does the opposite. Its solid body crawls, but its air moves at hurricane speeds that would circumnavigate our world in less than a day. Even more bizarre, Venus rotates backwards compared to almost every other planet, a slow retrograde spin, while its atmosphere races in the same direction. It is as if the planet's skin is stationary, but its gaseous cloak is being whipped around by some unseen cosmic force. So what engine drives this perpetual planet-wide tempest? The leading suspect is a complex interplay of solar heating and mysterious atmospheric waves. The sun constantly heats the atmosphere on Venus's day side. That hot air rises, races toward the cooler night side to sink back down, and is then swept along again. But this basic thermal circulation should not create such extreme, consistent speed. Scientists believe giant planet-spanning waves within the atmosphere itself, similar to vast undulations in an ocean of gas, may be transferring energy and momentum from the planet's slow spin-up into the fast-moving clouds, acting as a kind of continuous accelerator. The problem is our best supercomputer climate models, which beautifully simulate Earth's weather, consistently fail to recreate the ferocious, sustained power of Venus's superrotation. They either cannot get the winds fast enough or they cannot make them last. This tells us we are missing a fundamental piece of the physics puzzle, a hidden mechanism within that thick, toxic air that keeps this atmospheric engine revving at impossible speeds. Understanding it would not just solve a Venusian mystery, it would rewrite the textbook on how planetary atmospheres behave under extreme conditions. The planet's chaotic winds are not its only missing shield. While Earth is cocooned within a powerful global magnetic field, generated by the churning of its molten iron core, Venus stands utterly exposed. This is deeply puzzling. Venus is nearly Earth's twin in size and density, which strongly suggests it, too, possesses a large core of iron and nickel. Yet our sister world generates no planet-wide magnetic shield of its own. Without this protective bubble, Venus's thick atmosphere is left completely vulnerable to the relentless onslaught of the solar wind, that stream of charged particles constantly blowing from the sun. So why would two such similar planets have such dramatically different magnetic personalities? The leading suspect is one we have already met: Venus's incredibly slow rotation. On Earth, our planet's rapid 24-hour spin, combined with the convective motion of molten metal in the outer core, acts like a gigantic, self-sustaining dynamo. This geodynamo effect generates our protective magnetic field. Venus, however, takes 243 Earth days to complete a single turn. This sluggish rotation may simply be too weak to stir the planet's metallic core into the organized, turbulent motion needed to power a magnetic dynamo. It is like trying to spin a turbine with a gentle nudge instead of a vigorous crank. The mechanism fails to start, but rotation speed might not be the whole story. Some scientists propose that Venus's core might have cooled and solidified completely, leaving no molten layer to churn. Others suggest the core could be entirely molten but not convecting properly, perhaps because it is too thermally uniform, with heat distributed evenly so it does not rise and fall in the necessary currents. There is even a theory that the immense surface pressure, 90 times that of Earth, might somehow suppress the dynamo process. The implications of this missing shield are profound. Earth's magnetic field deflects the vast majority of the solar wind, channeling energetic particles harmlessly toward the poles to create our auroras. Venus has no such defense. The solar wind slams directly into the planet's upper atmosphere, slowly but steadily stripping it away. This relentless erosion might help explain why Venus, despite its runaway greenhouse, has an atmosphere that is still somewhat thinner than what some models predict for such a violent past. The solar wind is continuously sandblasting the planet's gaseous envelope into space, so we are left with a haunting image, a world with a heart that might be similar to our own, but one that either beats too slowly or has fallen silent, leaving its sky naked to the cosmic storm. While the solar wind strips away at the atmosphere, the ground below tells its own ancient and fractured story. across the scorching plains of Venus rise strange, rugged highlands unlike anything else on the planet. From orbit, radar maps reveal them as vast, complex regions of crisscrossing ridges and grooves, a chaotic texture that resembles cracked floor tiles. This appearance gave them their name, tesserae, from the Greek word for tiles. These are not young features. They are some of the oldest geological formations on Venus, preserved time capsules from a period billions of years ago when the planet's surface was being violently reshaped. On Earth, the most obvious analog for these elevated, highly deformed blocks of crust is our continents. This simple comparison sparks a monumental question. Could the tesserae be the remnants of ancient Venusian continents, standing above the lower volcanic plains like our own landmasses rise above the ocean floor? The possibility is electrifying because it suggests a Venus that was once far more dynamic and perhaps even more Earth-like than the static hellscape we see today. But how did these fractured highlands form? The debate is fierce and centers on the fundamental forces that once moved this world's crust. One school of thought points to massive, prolonged volcanic activity. Imagine flood after flood of thick, sticky lava slowly building up these regions layer by layer, with the weight of the rock causing it to fracture and fold under its own pressure. Another theory argues for intense crustal compression, as if the entire region was caught in a global vise, squeezed and crumpled upward into these ridged highlands. The most tantalizing idea, however, is that the tesserae are evidence of ancient, large-scale tectonic processes. On Earth, our continents are shaped by plate tectonics, where giant slabs of crust jostle, collide, and dive beneath one another. While modern Venus shows no signs of active Earth-style plate tectonics today, the tesserae could be the scarred fossils of a time when it did. Their complex deformation suggests multiple episodes of pushing, pulling, and shearing forces acting on the crust, a history written in ridges that our radar can read but cannot yet fully translate. This mystery makes the tesserae one of the highest priority targets for future missions. Their unique radar signature and elevated position mean they have been exposed to the atmosphere's corrosive chemistry and punishing pressure for eons, potentially recording a different geological history than the younger volcanic plains. To land a probe on these cracked highlands would be to land directly on the oldest pages of Venus's storybook, a chance to read the opening chapters of a world that chose a path so different from our own. What secrets of a lost, dynamic Venus are locked within those stone folds? Those ancient tesserae survived a planetary apocalypse. The rest of Venus was not so lucky. Radar maps from the Magellan mission revealed a surface covered in vast lava plains, punctuated by relatively few impact craters. This scarcity of craters is the first major clue. On geologically dead worlds like the Moon or Mercury, craters accumulate over billions of years, creating a densely pocked landscape. Venus has only about 1,000 large craters, and they are distributed in a seemingly random, almost pristine pattern. This points to a startling conclusion. The entire surface of Venus appears to be roughly the same age, an estimated 300 to 600 million years old. It is as if, in a relatively recent chapter of solar system history, the planet's face was completely remade, erasing nearly all traces of its previous 4.5 billion years. This is the theory of global volcanic resurfacing, a catastrophe of fire that buried the old Venus under a fresh skin of rock. But how did this happen? Scientists are divided into two competing schools of thought. The first is the catastrophic model. Imagine a planet where heat builds up relentlessly beneath a rigid, single plate of crust. With no plate tectonics to release that internal pressure gradually, the strain becomes unbearable. Finally, the entire planetary lid cracks open at once. Colossal plumes of superheated rock burst from the mantle, flooding the globe in a relatively short, violent spasm of volcanism. Lava oceans hundreds of miles across would have erased mountains, filled basins, and buried every older feature in a new, uniform layer of basalt. The alternative is the equilibrium model. This view suggests Venus does have a form of periodic, intense volcanic activity, but not all at once. Instead, different regions might experience catastrophic resurfacing in cycles, with the heat from the planet's interior managing to break through the thick crust in different places over hundreds of millions of years. The result would still be a young-looking surface on average, but the process would be more staggered and regional, not a single planet-wide event. The trigger for either scenario lies in Venus's unique internal plumbing. Without plate tectonics to act as a global cooling system, heat from radioactive decay builds up beneath an incredibly strong, unbroken lithosphere. Eventually, that heat must escape. On Earth, it leaks out constantly at mid-ocean ridges and subduction zones. On Venus, it may store up like a pressure cooker until the entire system violently blows its lid. This raises a profound and unsettling question. If such a global rebirth happened only a few 100 million years ago, could it happen again? Is the serene-looking Venus we see today merely in the calm between planetary-scale eruptions, quietly building up the heat for its next fiery transformation? Those ancient lava plains may not be as dormant as they appear. A growing body of evidence suggests Venus is not a geologically dead world, but one that might still be breathing fire. The first compelling clue came from the atmosphere itself. Missions have detected sudden, mysterious spikes in the concentration of sulfur dioxide, a gas closely associated with volcanic eruptions on Earth. These spikes appear and then fade, as if a hidden vent had just belched a plume into the clouds before shutting off again. While atmospheric circulation could theoretically concentrate the gas, these transient surges point to a fresh, intermittent source from below. Then there are the thermal fingerprints. Infrared observations from orbit have occasionally spotted regions on the surface that appear anomalously hot, glowing in the darkness of the long Venusian night. These hotspots are not distributed randomly. They often align with known volcanic features like large shield volcanoes or vast lava channels. The most tantalizing interpretation is that we are seeing the residual heat from recent, or even ongoing, lava flows cooling on the surface. Perhaps the most direct visual evidence comes from painstaking analysis of radar images taken years apart. Scientists have identified surface features that seem to have changed shape between observations. In a few locations, what once looked like a smooth, old lava flow appears to have been covered or altered by a newer, rougher flow, suggesting a volcanic event occurred in the intervening time. One of the most famous candidates is a volcano called Idun Mons, which shows signs of relatively fresh lava in its summit region. Confirming current volcanic activity would transform our understanding of Venus entirely. It would mean the planet is not just a fossil world, but a geologically alive one with a churning, hot interior still capable of reshaping its own crust. This ongoing activity is the key to unlocking the planet's thermal evolution, the story of how it has cooled and released its internal heat over billions of years. On Earth, our heat escapes steadily through plate tectonics. If Venus is volcanically active without moving plates, it forces us to invent new models for how rocky planets manage their energy. Is the heat escaping in sporadic, catastrophic bursts like the global resurfacing event, or through a more steady, localized trickle of eruptions? Each potential wisp of volcanic gas, each faint infrared glow, is a message from the planet's fiery heart, a clue that the story of Venus is still being written. Amidst the search for volcanic whispers, an announcement in 2020 sent shockwaves through the scientific community. Researchers reported the tentative detection of phosphine gas in the temperate cloud decks of Venus. On Earth, this simple molecule is almost exclusively produced by living organisms or human industry, making it a potential biosignature, a chemical hint of life. The idea was staggering. Could floating microbial life exist in the balmy, acidic droplets of Venus's upper atmosphere, a habitable pocket in an otherwise hellish world? The initial excitement was electric, promising a radical rewrite of our search for life in the cosmos. But science is a process of relentless scrutiny, and the phosphine story quickly became a masterclass in that rigorous debate. Other teams re-examined the data using different telescopes and analysis methods. Some could not find the phosphine signal at all. Others suggested the original detection might have been confused by a more common atmospheric gas, sulfur dioxide, or was the result of statistical noise in the incredibly complex data. Alternative, non-biological explanations were proposed, including exotic chemical reactions involving volcanic minerals lofted into the clouds, or previously unknown atmospheric chemistry driven by the planet's extreme conditions. The controversy highlighted two profound truths. First, the environment within Venus's clouds is so alien, so poorly understood, that we cannot yet rule out bizarre, non-living chemical pathways that might produce phosphine. Second, it underscored the immense challenge of astrobiology. A single, tantalizing signal is never enough. It must be confirmed, reconfirmed, and all other explanations must be exhaustively ruled out before we can whisper the word life. While the phosphine detection remains in doubt, the fervent investigation it sparked has permanently elevated the astrobiological profile of Venus's clouds. We are now forced to ask with renewed seriousness, in an environment of sulfuric acid and strange chemistry, what truly is impossible? The search for phosphine forces us to confront a much older and more profound question. Could life, in some unimaginable form, not only exist but actually thrive in the skies of Venus? This is the hypothesis of an aerial biosphere, a concept that transforms the planet's greatest danger into a potential sanctuary. High above the crushing pressure and furnace-like heat of the surface, between roughly 30 and 40 miles in altitude, lies a temperate zone. Here, the temperatures are surprisingly Earth-like, ranging from about 30 to 170 degrees Fahrenheit. The pressure is comparable to sea level on our own world. It is within this narrow, floating band that scientists have long speculated life could theoretically persist. The idea is not that creatures fly through the clouds, but that microscopic extremophile organisms could live inside the suspended droplets of the Venusian clouds themselves. On Earth, we find bacteria thriving in our own atmosphere, inside acidic hot springs, and in environments with almost no water. The proposed Venusian microbes would need to be the ultimate extremophiles, evolved to withstand a bath of concentrated sulfuric acid, the primary component of the cloud droplets. They would need a biochemistry that functions without liquid water as we know it, perhaps using the sulfuric acid itself as a solvent, or existing in a dormant state until a droplet provides a fleeting, habitable moment. The life cycle imagined is hauntingly beautiful. A microbe would live, metabolize, and reproduce inside a droplet. As that droplet grows larger, it would eventually fall through the atmosphere into the hotter, lethal layers below. But just before the organism is destroyed, the intense heat would evaporate the droplet, leaving the desiccated but still viable microbe to be lifted back up by atmospheric currents into the temperate zone, where it would become the nucleus of a new, life-bearing droplet. This speculative cycle turns the entire corrosive cloud deck into a vast recycling habitat. The challenges, of course, are monumental. Beyond the acidity, the clouds are desperately dry, with a water vapor concentration thousands of times lower than in Earth's air. Any biochemistry would have to operate with almost no water at all. There is also the constant bombardment of ultraviolet radiation from the sun, though the upper cloud layers themselves could provide some shielding. To move from speculation to evidence, we need to go there and look. This is the driving purpose behind upcoming missions like DAVINCI and VERITS. DAVINCI is a daring probe designed to plunge through the atmosphere, sampling its chemistry with every mile of descent. It will measure trace gases, including any potential organic molecules or other biosignatures, with unprecedented precision, and even take the first high-resolution photos of the Tesserae highlands during its descent. VERITAS, an orbiter, will map the planet's surface and subsurface with powerful radar, looking for the telltale heat signatures of active volcanism and mapping rock composition to understand if volcanoes are lofting nutrients into the clouds that could support an aerial ecosystem. Together, they will not search for little green men, but for the chemical and geological context that could make a cloud-based biosphere possible. They seek to answer whether this floating, acidic environment is merely a bizarre geologic phenomenon or a universe-expanding revelation, a habitat for life in one of the last places we ever thought to look. For centuries, observers peering through telescopes have reported something haunting on the darkened face of our sister world. When Venus presents its night side to Earth, a faint, ghostly illumination sometimes appears to stain its shadowed crescent. This is the ashen light, a pale glow akin to the soft luminescence we see on Earth's own dark side, called Earthshine, where sunlight reflected from our planet gently lights up the moon. But Venus has no large moon to cast such a glow. The light seems to come from Venus itself, an enigmatic radiance from within its perpetual cloud cover. Historical accounts date back to the 1600s, with famed astronomers like Giovanni Cassini documenting the phenomenon. Descriptions often speak of a dim, uniform, grayish or coppery light, subtly illuminating features that should be plunged into utter darkness. It is an intermittent mystery, appearing and vanishing without any predictable pattern, which only deepens its intrigue. So what could possibly be lighting up the night side of a world shrouded in toxic clouds? Scientists have proposed several compelling yet unproven explanations. One leading idea points to intense electrical activity in the Venusian atmosphere. If powerful, planet-wide lightning storms were constantly flashing within those thick clouds, the collective glow from countless discharges might create a faint, diffuse illumination visible from space, a perpetual silent storm lighting up the night from within. Another theory involves a chemical airglow, a process where atoms and molecules in the upper atmosphere, excited by solar radiation during the day, release that stored energy as a soft light after sunset. On Earth, we see similar faint glows in our own night sky. On Venus, with its alien atmospheric chemistry, such an airglow could be far more pronounced. There is also the possibility of a more exotic electrical phenomenon, a Venusian version of an aurora, generated not by a global magnetic field but by interactions between the solar wind and the planet's ionosphere, painting the night sky with ethereal light. Yet, for all these plausible theories, the ashen light remains stubbornly elusive to modern science. Our most advanced spacecraft and instruments, sent to orbit and probe Venus, have never conclusively captured or confirmed the glow. This leads some to argue it may be nothing more than a persistent optical illusion, a trick of contrast as the eye strains against the brilliant, sunlit crescent, causing the brain to fill in the dark portion with a phantom light. But the consistency of reports from experienced observers over hundreds of years suggests something more is at play. The ashen light stands as a testament to the limits of our remote sensing, a whisper from the shadows of Venus that modern technology has yet to fully hear, a gentle reminder that some mysteries require a human eye, patient and wondering, to keep their story alive. The ghostly ashen light is a mystery of perception, but the chemical fingerprint etched into Venus's atmosphere reveals a far more concrete and devastating loss. This evidence points to a time when Venus was not a desiccated hellscape, but a world that may have held vast, shimmering oceans. The key to this vanished water lies in a subtle difference between two forms of hydrogen. Ordinary hydrogen has a single proton in its nucleus. A heavier version, called deuterium, has a proton and a neutron. In Earth's oceans, for every million atoms of ordinary hydrogen, there are about 150 atoms of deuterium. On Venus, the ratio is staggeringly different. Measurements show the atmosphere is massively enriched in heavy deuterium, with over 100 times more deuterium relative to ordinary hydrogen than we find on Earth. This imbalance is a forensic clue of epic water loss. Here is how the crime unfolded. If Venus once had surface water, sunlight would have warmed it, causing evaporation. Water vapor, a potent greenhouse gas, rose into the upper atmosphere. There, fierce ultraviolet radiation from the sun broke the water molecules apart, splitting them into hydrogen and oxygen. The lightweight ordinary hydrogen, unburdened by an extra neutron, escaped easily into the vacuum of space, carried away by the solar wind. The heavier deuterium, however, struggled to achieve escape velocity. Over billions of years, as countless trillions of water molecules were destroyed, the ordinary hydrogen fled, while the deuterium was left behind, becoming more and more concentrated in what remained. The current ratio is like finding a single, dense gold coin at the bottom of an emptied treasure chest, a testament to the immense wealth that was once there. Scientists estimate Venus may have lost an ocean's worth of water, a volume that could have covered the entire planet to a depth of hundreds of feet. This leads to the catastrophic question: what triggered the initial evaporation that doomed the planet? The culprit was likely a runaway greenhouse effect, sparked by Venus's slightly closer position to the Sun. As the Sun grew brighter over its lifetime, Venus's early oceans may have begun to simmer. More water vapor entered the atmosphere, trapping more heat, which evaporated more water. This positive feedback loop spiraled out of control, boiling the oceans entirely and leaving a thick, steamy atmosphere. With no liquid water left to absorb carbon dioxide from the air through rock weathering, that greenhouse gas built up relentlessly from volcanic outgassing, creating the crushing, heat-trapping blanket we see today. The high deuterium ratio is more than a chemical curiosity. It is the lasting signature of a planetary-scale climate catastrophe, a warning written in the atoms of a dying sky. It tells us that a world can cross a threshold from which there is no return, its life-giving water forever stripped away by the very star that gave it light. The story of water is not the only chemical secret locked in Venus's air. Scientists have found that the very building blocks of the atmosphere, the noble gases, tell a conflicting and confusing tale. These gases, like argon and xenon, are chemically inert. They do not react with other elements or get locked into rocks, making them perfect time capsules from the planet's violent birth. On Earth, we have a specific mix of these noble gas isotopes, a kind of elemental fingerprint. Mars has its own distinct fingerprint. Venus, however, presents a set of ratios that match neither Earth nor Mars and defy our standard models of how rocky planets in our neighborhood should have formed. This is a fundamental mystery of provenance. If Venus, Earth, and Mars all coalesced from the same primordial cloud of dust and gas around the young Sun, why do their most primitive atmospheric ingredients look so different? One possibility points to a dramatic difference in how these worlds collected their early atmospheres. Perhaps Venus formed from material that was inherently different in its isotopic composition, a pocket of the solar nebula with a unique signature. Another, more dynamic theory involves colossal impacts. The early solar system was a shooting gallery with planet-sized bodies smashing into each other. A giant impact on Venus could have stripped away its original atmosphere entirely. The atmosphere we see today would then be a second-generation blanket, outgassed later from the planet's interior, carrying a different isotopic mix than the one it started with. There is also the puzzle of xenon. Venus has an unusually high amount of a light isotope of xenon compared to heavier ones, a pattern that is the opposite of what we see on Earth. This could be a clue about the timing and process of atmospheric escape, suggesting hydrogen loss in the ancient past dragged some lighter noble gases with it, or it could indicate a source of gases from the deep mantle that we do not fully understand. These strange ratios are more than a chemical curiosity. They are direct messages from the first 1% of the solar system's history, challenging the neat story that the inner planets are simple siblings. They force us to ask whether Venus was always the odd one out, born in a different part of the stellar nursery, or if it suffered a traumatic childhood impact so severe it reset its entire atmospheric identity, leaving us to decipher the clues of a crime 4.5 billion years cold. These strange noble gases whisper of a chaotic birth, but the surface they now envelop tells a story of immense and patient construction. Towering over the fractured tesserae and vast lava plains are the crown jewels of Venusian geology, colossal shield volcanoes that dwarf nearly every mountain on Earth. The most famous is Mont Mons, a behemoth that rises 5 miles above the surrounding plains, with a base stretching hundreds of miles across. To stand on its summit would be to stand on the peak of a mountain wider than the state of Arizona, a gentle slope built not of jagged rock but of countless fluid lava flows stacked over eons. Nearby, Sopper's Mons stands almost as tall, a twin titan of fire. These are not the steep, explosive cones we often picture. They are shield volcanoes, named for their broad, low profile that resembles a warrior's shield lying on the ground. Their immense size poses a fascinating question. Why did they grow so unimaginably large? The answer lies in a key difference between Earth and Venus, the absence of plate tectonics. On our planet, the crust is broken into moving plates. A hot spot of upwelling magma from the mantle will punch through the crust to create a volcano, like the one that formed the Hawaiian Islands. But as the Pacific plate slowly drifts northwest, the hot spot stays in place, creating a chain of volcanoes, each one aging as it moves off the plume. The Big Island of Hawaii is the current active product. On Venus, there are no moving plates. The crust is a single global lid. So when a massive mantle plume rises and finds a weak spot, it stays put. For hundreds of millions of years, magma from that same stationary hotspot erupts onto the surface, layer upon layer, flow upon flow, all piling up in one location. Without a plate to carry it away, the volcano just keeps growing, becoming a monstrous, singular edifice. This makes Mont Mons not just a mountain, but a geological record player, with its oldest lava flows at the base and potentially the youngest at its summit. So are these giants still alive? The search for recent heat signatures and fresh lava flows often focuses on these very volcanoes. If their underlying mantle plumes are still active, they could be the source of the transient hotspots and sulfur dioxide spikes we detect. Their composition is another vital clue. By analyzing the radar signatures of the lava that built them, scientists can infer what the magma was made of. Was it runny, basaltic lava like that which builds Hawaii, or something thicker and more silica-rich? The answer tells us about the temperature and chemistry of Venus's deep mantle, the engine room of the planet. These quiet titans are not just scenery, they are direct pipelines to a hidden interior, standing as permanent monuments to the patient, planet-altering power of a world that chose to build its mountains in one place forever. While massive volcanoes build mountains in one spot, other parts of Venus release their internal heat in stranger, more artistic forms. Scattered across the radar maps are hundreds of peculiar features called coronae, singular corona. These are not impact craters or volcanoes in the traditional sense. They appear as vast, circular or oval bullseyes, sometimes hundreds of miles across, marked by a complex pattern of concentric rings and fractures. Picture a giant stone dropped into a pond of molten rock, freezing the ripples in place, and you begin to grasp their otherworldly appearance. These enigmatic structures are a signature feature of Venus, with no true equivalents found on Earth, Mars, or anywhere else in our solar system. Their uniqueness makes them a critical clue to understanding how this world manages its internal fire. Scientists believe coronae are the surface fingerprints of massive upwelling plumes of hot rock rising from the deep mantle. As this blistering material nears the surface, it pushes the crust upward into a broad dome. But the thick, strong lithosphere of Venus resists this pressure. Eventually, the dome might collapse under its own weight, or the plume might retreat, causing the center to sink back down. This pushing, stretching, and collapsing process creates the characteristic rings and fractures, a frozen record of a titanic subterranean struggle. This makes coronae a potential key to a planetary puzzle, the mystery of stagnant lid tectonics. Unlike Earth's mobile plates, Venus has a single, unbroken global lid of crust. Coronae may represent how this stagnant lid locally thins, warps, and cracks to let heat escape without the crust ever breaking into moving pieces. They could be planetary pressure valves. This connects them directly to the great mystery of global resurfacing. If Venus's heat builds up catastrophically under its rigid shell, could these coronae be the precursors to a planet-wide rupture? Do they represent a more gentle, ongoing release of heat that prevents a total catastrophe, or are they the first cracks that appear before the entire lid shatters in a resurfacing event? Each corona is a fossilized thermal pulse, and by counting them, measuring their sizes, and studying their states of erosion, scientists hope to read the rhythm of Venus's internal heartbeat, to learn whether this world cools itself in a steady whisper or a pent-up planetary scream. The fractured rings of coronae are not the only cryptic patterns etched into Venus's crust. Radar maps reveal even stranger, more delicate architectures, features that look less like geology and more like something spun from a nightmare. These are the arachnoids and nova, names that perfectly capture their unsettling appearance. Arachnoids, from the Greek word for spider, are circular features surrounded by a complex web of fine, radial fractures that stretch outward like the legs of a monstrous insect. Nova, meaning new stars, are bright, starburst-shaped centers from which long, linear fractures radiate in every direction, as if the ground itself had been struck from below by a colossal, pointed force. Both are testaments to a world where the crust is not just broken, but intricately cracked by pressures from the unseen depths below. Their formation is a story of subterranean force meeting a brittle shell. Scientists believe these features are created by diapirs, blobs of buoyant, semi-molten rock that rise through the mantle like blobs of wax in a lava lamp. As a diapir nears the surface, it pushes upward on the overlying crust, doming it and stretching it to its breaking point. The resulting stress field creates these precise, radial fracture patterns, a frozen snapshot of the crust cracking under concentrated pressure. The exact shape, whether it becomes a spidery arachnoid or a stark nova, likely depends on the depth, size, and viscosity of the intruding diapir, and the thickness and strength of the crust at that exact spot. These are not random cracks, they are intricate blueprints of force. By studying their delicate patterns, planetary geologists can perform a kind of forensic engineering on Venus. The spacing, length, and arrangement of the fractures reveal crucial information about the mechanical properties of the Venusian crust at the time it fractured, how brittle it was, how much stress it could withstand before snapping. They are natural stress gauges permanently recording the moment of failure. Their presence, often in clusters or associated with coronae and volcanoes, paints a picture of a planet where magmatic pressure is constantly testing the limits of its global lid, not with broad, catastrophic ruptures, but with thousands of localized, precise experiments in fracture mechanics. In their eerie, web-like beauty, the arachnoids and nova show us a world under constant, delicate strain, its skin etched with the signatures of restless forces that have never ceased their push toward the surface. This delicate, fractured crust supports mountains that reach into a sky filled with impossible weather. At the very peaks of the tallest ranges, like the towering Maxwell Montes, the Venusian environment performs one of its most bizarre tricks. Radar maps reveal something startling. These high elevations are exceptionally bright, reflecting radar signals back with a mirror-like shine. In the crushing heat and corrosive air of Venus, what natural substance could create such a pristine, glittering cap? The leading answer is as strange as the planet itself: metallic snow. Not the frozen water we know, but a frost of minerals that behave like metals, condensing directly from the scorching atmosphere onto the cold mountain tops. Here is how this alchemy works. Certain metallic minerals such as pyrite, often called fool's gold or bismuthinite, can vaporize at the extreme temperatures found on the lower plains and valleys of Venus. Carried by the super-rotating winds, these metallic vapors rise into the upper reaches of the atmosphere. As they reach the high altitudes of the great mountain ranges, the temperature plummets. It is still brutally hot by Earth standards, but cool enough for a remarkable phase change. Just as water vapor in our air condenses into frost on a cold window pane, these metallic vapors condense directly into a solid, crystalline frost on the mountain slopes and summits. This would create a thin, glittering coating of metallic snow, a substance that would be highly reflective to both radar and, hypothetically, visible light. This theory elegantly explains the mysterious radar brightness. It also paints a surreal picture: the highest peaks on a hellish world, bathed in a perpetual, toxic twilight, might be crowned with a shimmering, metallic frost that slowly sublimates back into vapor on the sunward side, only to condense again in the shadows. It is a weather cycle forged in a furnace where the snow is never wet and the mountains wear crowns of fool's gold. This metallic snow falls in a world of profound electrical silence, or so we once thought. But the clouds of Venus may crackle with a power all their own. For decades, scientists have debated whether our sister planet experiences lightning, a phenomenon that would dramatically alter our view of its dynamic, hidden skies. The first clues came from the Soviet venera-landers as they descended through the thick atmosphere. Their instruments picked up peculiar low-frequency radio waves called whistlers, eerie signals that on Earth are the unmistakable fingerprint of distant lightning strikes. These waves are created when a lightning bolt generates a burst of electromagnetic energy that travels along planetary magnetic field lines, its frequency shifting as it goes, producing a distinctive falling tone. The venera detections were tantalizing but not conclusive proof. Later, the European Space Agency's Venus Express orbiter added another piece to the puzzle. It observed sudden, powerful bursts of electromagnetic energy in the planet's atmosphere, bursts that again looked very much like the signatures of lightning. If real, this would not be the gentle flicker of a summer storm, but likely immense, continuous discharges within the global cloud deck. The challenge, however, is fundamental. On Earth, lightning is intimately tied to water. Our thunderstorms rely on the friction between ice crystals and water droplets within towering cumulonimbus clouds to separate electrical charge, building up the tremendous voltage that eventually arcs across the sky. Venus has no water clouds. Its skies are a perpetual haze of sulfuric acid droplets. So how could lightning possibly form in such an alien, dry environment? This puzzle has sparked a fierce scientific debate. One possibility is volcanic lightning. If Venus is indeed volcanically active, as suspected, immense plumes of ash and rock particles ejected into the atmosphere could collide and generate static electricity through friction, just as ash clouds do during terrestrial volcanic eruptions. This would be a dry lightning, unconnected to water, flashing in the gloom above fiery peaks. Another theory suggests the complex chemistry of the sulfuric acid clouds themselves might be enough. The droplets, composed of different concentrations of acid and water, might collide and separate charge through a process we do not yet fully understand. There are even proposals for exotic mechanisms involving the solar wind interacting directly with the upper atmosphere to create electrical discharges. The stakes of this mystery are high. Confirming lightning on Venus would do more than add dramatic weather to its resume. It would have profound implications for the planet's atmospheric chemistry. The immense energy of a lightning bolt can break apart stable molecules, triggering chains of chemical reactions that would not otherwise occur. It could be a factory for producing new, complex compounds in the atmosphere, potentially even the kind of organic molecules that are the precursors to life. Each unexplained whistler wave, each electromagnetic burst, is a potential flash illuminating the hidden workings of a world that refuses to be simple. challenging us to rethink the very ingredients needed to electrify a sky. Above the crackle of potential lightning, an even larger and more serene mystery floats in the ultraviolet view of Venus. For decades, telescopes and spacecraft have captured a persistent, planet-spanning formation in the upper cloud decks, a vast and unmistakable Y-shaped pattern. This is not a temporary storm or a random swirl. It is a permanent fixture in the churning sky, a colossal atmospheric wave frozen in time. When viewed in ultraviolet light, which highlights contrasts in the cloud tops, this dark Y seems painted across the face of the planet, its arms stretching across the equatorial regions and meeting at a point near the poles. The most astonishing fact is its stability. While the clouds themselves race around the planet in the super-rotation, this Y pattern remains fixed relative to the Sun. It does not move with the wind, it stands still against the hurricane, always pointing its apex toward the subsolar point, the spot directly under the Sun. This reveals its true nature. It is a stationary wave, a standing ripple in the fluid of the atmosphere, generated by the constant push of solar heating. Imagine ocean waves crashing against a seawall and rebounding, creating a pattern that churns in place. On Venus, the Sun's intense heat acts like that constant push on the dayside atmosphere. This heating interacts with the planet's fast-moving winds and its slow retrograde spin, setting up a resonant vibration, a planetary-scale wave that simply cannot travel, so it holds its shape. This Y is the visible expression of that resonance, a harmonic in the global weather system. Its stability is its greatest clue. For such a pattern to hold against the chaotic, super-rotating winds, the forces that create it must be perfectly balanced and incredibly powerful. It acts as a permanent heat distributor, a conveyor belt in the sky that helps transport the blistering solar energy from the equator toward the cooler poles, playing a crucial role in regulating the planet's ferocious climate. Understanding this wave is like finding the fundamental frequency of Venus's atmosphere, a key to unlocking the complex physics that keeps its entire weather machine in motion. If we can finally model how this Y forms and persists, we will have deciphered one of the master controls for the most alien climate in our solar system. That colossal Y-shaped wave channels the planet's ferocious heat toward its poles, where the atmosphere performs its final and most hypnotic act. At both ends of Venus, massive, permanent hurricanes swirl in the perpetual darkness, but these are not simple storms. The Venus Express mission revealed them to be bizarre, double-eyed vortices, each one a pair of swirling lobes dancing around one another in a complex, shifting duet. Earth has its own polar vortices, cold pools of swirling air locked over the Arctic and Antarctic during winter, but they are relatively simple and temporary features. Venus offers something entirely different, a permanent, dynamic whirlwind with two distinct centers of rotation. Imagine a colossal figure 8 drawn in the clouds, constantly churning and morphing, its shape changing from day to day, sometimes appearing as two separate eyes, other times merging into a squashed, peanut-like form. This double vortex is the final destination for the super-rotating winds. As the hurricane-speed atmosphere races from the equator toward the poles, it converges and begins to sink. But the planet's slow spin and the complex topography below disrupt this descent, forcing the air to spiral into these unstable, double-lobed formations. They are immense engines of atmospheric mixing, where chemicals from different cloud layers churn together and heat is redistributed in the planet's final act of global circulation. Yet for all their grandeur, we barely understand their rules. Their shape is notoriously variable, changing in ways our computer models cannot yet predict. What determines whether the vortex splits into two clean eyes or merges into a single, distorted mass? The answer lies in the intricate and unseen interplay between the sinking air, the planet's gentle rotation, and even the subtle influence of mountains and highlands far below, which may nudge the flow in unexpected ways. These polar vortices are more than just weather. They are the chaotic, beating hearts of the Venusian climate system, a mesmerizing puzzle of fluid dynamics spinning in the frozen dark. The hypnotic dance of the polar vortices is set to a clock we are still trying to read. Even something as fundamental as the length of a Venusian day has proven to be a shifting, elusive target. For decades, scientists firing radar signals at the planet have watched in puzzlement as their measurements of its rotation period refused to agree. One study would find a day lasting 243.02 Earth days, while another, conducted years later, would show a slightly different value, perhaps 243.025 days. The discrepancies were small, mere fractions of a second per Venus day, but they were real and persistent. This was not a case of faulty instruments, it was the planet itself changing its pace. The culprit is a breathtaking exchange of momentum between the planet's two most dominant features, its sluggish, solid body and its hurricane-speed atmosphere. That thick, fast-moving blanket of gas is not just sliding over the surface, it is physically interacting with it, pushing and pulling on mountain ranges and vast plains through friction and pressure differences. Think of it as a planetary scale tug-of-war. The super-rotating atmosphere screaming around the planet is constantly trying to drag the ground along with it to speed up its rotation. At the same time, the massive, rocky bulk of Venus resists, its immense inertia fighting to stay at its own slow, steady pace. The result is a delicate, ongoing transfer of angular momentum, the same principle that causes a spinning ice skater to speed up when they pull their arms in. As momentum shifts from the air to the rock or back again, the planet's rotation actually speeds up or slows down by a tiny, measurable amount. This discovery transforms our understanding of Venus from a static globe to a dynamic system where the sky and the ground are locked in a constant, forceful embrace. Measuring these subtle changes in the length of a day is not just about keeping time, it is a direct probe into the planet's hidden interior. The way the solid planet responds to this atmospheric pushing tells us critical details about its internal structure. If the core is molten and fluid, it might slosh slightly, absorbing some of the push in a different way than if the entire interior were solid rock. By tracking the rotation over many years, scientists can begin to model the planet's moment of inertia, a measure of how its mass is distributed deep inside. Is it concentrated in a dense core or more spread out? This deep coupling between atmosphere and interior is unique in our solar system, a continuous dialogue of forces written in the slowing and speeding of a world's spin. Each new, precise measurement of a Venusian day is like taking the planet's pulse, feeling for the subtle heartbeat of a system where the air itself has the strength to move mountains, and the mountains have the weight to hold the sky at bay. This celestial tug-of-war over rotation is a luxury Earth never had to manage, thanks to our own massive, stabilizing companion. But look to Venus and you find a sky empty of any such partner. Our sister world is utterly moonless, a solitary wanderer in its orbit around the sun. This absence is a silent mystery, a clue to a past that may have been even more violent than the planet's present. In our solar system, moons are the rule, not the exception. Every other planet, from gas giants to rocky Mars, has at least one natural satellite. Mercury, the other moonless inner planet, shares this lonely status with Venus. So why did our twin end up alone? One possibility is simply that Venus never acquired a moon in the first place. During the chaotic era of planetary accretion, when worlds were built from countless collisions, the region near the Sun may have been too dynamic, with gravitational forces too fierce, for a stable disk of debris to coalesce into a satellite around the growing Venus. The material was either swallowed by the planet or scattered away. A second, more dramatic theory involves a colossal impact. Earth's moon is widely believed to have formed from the debris of a cataclysmic collision between a young Earth and a Mars-sized protoplanet called Theia. Venus, being so similar in size and location, almost certainly experienced its own share of giant impacts, but the outcome could have been tragically different. If a similar impactor struck Venus, the resulting debris disk might have been too close to the Sun, where solar gravitational tides were too strong, preventing the material from clumping together into a stable moon. The shattered remains would have simply spiraled back down to the planet or been blown into space. An even more extreme version of this idea suggests an impact so perfectly aligned or powerful that it completely reversed Venus's rotation, leaving no coherent debris ring at all. The planet's slow, backward spin is often cited as potential evidence for such a world-shattering event. Finally, there is the delicate balance of orbital mechanics. For a moon to remain in a stable orbit around a planet, it must reside within a gravitational sweet spot called the Hill sphere. Inside this region, the planet's gravity dominates over the Sun's. Venus, orbiting closer to the Sun than Earth, has a much smaller Hill sphere. This makes it far harder for a moon to find a stable home, as the Sun's relentless pull would constantly tug at it, eventually either stripping it away or sending it crashing down. The moonless state of Venus speaks volumes about its infancy. It suggests a childhood of extreme violence where either no companion could peacefully form, or any that did was brutally taken away. This loneliness may have had profound consequences. Earth's moon acts as a gravitational anchor, stabilizing our axial tilt and moderating our climate over eons. Without that steadying hand, Venus's tilt could have been wildly erratic in its youth, leading to extreme climate swings that might have helped trigger its runaway greenhouse. Its empty sky is not just a quiet fact, but a monument to a past of cosmic chaos, a solitude born from fire. The profound loneliness of Venus makes the brief moments we touched its surface all the more extraordinary. In the 1970s and 80s, humanity achieved the impossible, landing robotic emissaries on that scorching, crushing world. The Soviet Union's Venera program succeeded where no one else dared, sending a series of landers that plunged through the acidic clouds and survived for a few precious minutes on the ground. These were engineering marvels, built like titanium submarines to withstand pressures 90 times Earth's, and encased in cooling systems to delay their inevitable overheating. Venera 9 transmitted the first ever grainy photograph from the surface of another planet, revealing a rocky, desolate landscape under a dim, orange sky. Others followed, taking soil samples and measuring the corrosive chemistry of the air, but their triumphs were heartbreakingly brief. The longest survivor, Venera 13, functioned for just over 2 hours before the relentless heat and pressure silenced its signals forever. So what became of these brave little machines after their transmissions stopped? We can only speculate based on the environment they were designed to resist. The sulfuric acid rain, though it evaporates before hitting the ground, exists as a corrosive mist in the lower atmosphere. Over decades, this would have slowly eaten away at their metal hulls and any exposed instruments, likely leaving them pitted and degraded. The immense atmospheric pressure, equivalent to being 3,000 feet deep in an ocean on Earth, would have continuously squeezed every seam and component. And the heat, a constant 860 degrees Fahrenheit, would have baked their internal electronics into inert, melted lumps long ago. They are almost certainly not functioning, and likely not even recognizable as the sophisticated probes they once were. Yet the very hell that destroyed them might also preserve a strange kind of relic. If the acid corrosion created a protective crust, or if internal components were sealed perfectly, it is conceivable that some hardened artifacts, like the titanium pressure spheres or ceramic parts, might still exist in situ, slumped on the basalt plains. They are monuments to human ingenuity in the most hostile environment we have ever explored. Their silent forms waiting on a world where no wind will ever cover them with dust. Those silent venera-landers captured a stark and honest truth, a world of rock and sky. Yet when we look at other images of Venus, our own human minds sometimes see something more. This brings us to a fascinating psychological mystery that has touched nearly every world we have explored, the phenomenon of pareidolia. This is our brain's innate tendency to find familiar patterns, especially faces, in random shapes and textures. It is why we see a man in the moon or a camel in a cloud. Venus, with its global cloak of clouds hiding the surface, largely escaped this until radar pierced the veil. The Magellan mission in the 1990s mapped the entire planet with radar, revealing a landscape of volcanoes, plains, and fractures. In a few of these radar images, some observers have pointed to unusually angular shapes, features that, when viewed from a specific angle and with a certain contrast, can appear startlingly geometric. Online, you can find claims of vast pyramids, ruined cities, or even massive, face-like structures etched into the Venusian highlands. The most famous example is not from Venus but from our neighboring Mars, where a 1970s Viking orbiter image of a mesa in the Cydonia region, under specific lighting, looked uncannily like a human face staring upward, sparking decades of speculation about ancient Martian civilizations. On Venus, similar claims arise from our pattern-seeking brains interpreting the rugged, radar-bright edges of weathered volcanoes or the sharp intersections of tectonic fractures as something deliberately built. The scientific perspective is clear and grounded in geology. Venus is a world of extreme natural forces. Its surface has been shaped by unimaginable volcanic outflows, tectonic crumpling, and corrosive winds. A cluster of steep-sided volcanoes seen from above in low-resolution radar can easily create a cluster of pyramid-like shapes. Parallel ridges from crustal stretching can look like paved roads. There is no need for architects, only for the relentless, chaotic work of planetary physics. This does not make the images any less intriguing, but it reframes the mystery from one of alien engineers to one of human perception. The lesson of pareidolia is not a dismissal of wonder, but a celebration of scientific rigor. It highlights the crucial step in exploration where initial, exciting recognition must be followed by careful analysis. Scientists must ask, does the feature hold its strange shape from every angle, under every lighting condition, and at higher resolution? For every face or pyramid, the answer has always been no. The angles soften, the lines blur, and the structure resolves into a natural landform. This process is the bedrock of critical thinking, the essential filter that separates compelling stories from verified facts. It reminds us that the universe is strange enough on its own, filled with naturally occurring wonders far more bizarre and magnificent than any illusion we might project upon it. Our desire to see familiar shapes in the alien landscape is a testament to our curiosity, but our method for discerning the truth is what turns that curiosity into understanding. Yet the superrotation is not the only wind shaping that alien sky. Buried within the planet's racing cloud decks, scientists have found evidence of a more focused and powerful river of air, a high-altitude equatorial jet stream. Imagine a narrow, screaming band of wind confined to the planet's tropical regions, moving even faster than the already hurricane-speed clouds around it. This is not a gentle breeze, it is a stratospheric torrent, and its existence adds a crucial layer of complexity to Venus's atmospheric engine. The evidence comes from painstakingly tracking the subtle movements of different cloud layers over time. By observing how distinct features in the ultraviolet and infrared views drift, researchers can map wind speeds at various altitudes. What they found was a striking acceleration right at the cloud tops near the equator, a concentrated fast lane embedded within the broader super-rotating flow. This jet stream does not act in isolation. It is deeply entangled with the planet's other great atmospheric mysteries. It likely plays a key role in shaping and maintaining the vast, stationary Y-shaped pattern we see in the ultraviolet, acting as a kind of high-speed conveyor belt that helps lock that planetary wave in place against the sun. Furthermore, its energy must be fed by, and in turn influence, the overall momentum of the super-rotation, creating a layered system of winds where energy is constantly transferred between different altitudes and latitudes. Understanding this jet is not just about cataloging another weather pattern. It is absolutely critical for building a climate model that actually works. Our current computer simulations of Venus consistently fail to replicate the observed wind speeds and patterns with full accuracy. A major reason is that they cannot properly account for the intricate, layered interactions between phenomena like the equatorial jet, the superrotation, and the polar vortices. Each of these features represents a different way the atmosphere moves and redistributes the immense heat from the sun. To solve the energy balance of Venus, to create a model that can predict its weather and explain its past, we must first decipher how these wind systems exchange energy and momentum. The equatorial jet is a vital piece of that planetary power grid, a high-speed current in a global circuit we are only beginning to map. All these swirling mysteries of wind and fire lead us to a single central question. What lies at the heart of Venus, the planet's internal structure, is the ultimate locked box, the master key to its volcanic fury, its missing magnetic shield, and its entire catastrophic history. Without the ability to peer directly inside, scientists must become cosmic detectives, piecing together clues from the subtle ways the planet moves and interacts with space. The primary evidence comes from painstaking measurements of Venus' gravity field. By tracking how a spacecraft's orbit is minutely tugged and accelerated by the planet's mass, researchers can map the distribution of that mass deep below the surface. These maps reveal where the planet is denser or less dense, hinting at massive mantle plumes, sunken basins, or towering highlands with deep roots. Combined with precise tracking of the planet's wobbling rotation and its sluggish spin, these gravity data let us calculate the planet's moment of inertia, a number that tells us how its mass is arranged. Is it concentrated in a dense, compact core or spread more evenly throughout a larger volume? The answer points toward a core of iron and nickel, similar in size to Earth's, constituting roughly a quarter of the planet's mass. But here the mystery deepens. Is that core solid or liquid? The lack of a global magnetic field is the crucial, contradictory clue. On Earth, our magnetic dynamo is powered by the churning convection of molten iron in the outer core, driven by the planet's rapid rotation. Venus has the raw material, a likely iron core, but its rotation is impossibly slow. This suggests one of three possibilities. First, the entire core may have cooled and solidified completely, a frozen, metallic heart with no moving parts to generate a field. Second, the core could be entirely molten but not convecting, perhaps because it is too thermally uniform, with heat distributed evenly so it does not rise and fall in the necessary currents to drive a dynamo. The third and most Earth-like possibility is a layered core with a solid inner sphere surrounded by a liquid outer shell, but one that is simply too sluggish or stable to produce magnetic turmoil. Determining which state is true is not an academic exercise, it is the foundation for every other story about Venus. A solid core suggests a world that has lost most of its internal heat, its volcanic activity a fading echo of a more violent past. A molten, convecting core, even a quiet one, implies a world still hot and dynamic beneath its thick crust, potentially fueling ongoing eruptions and storing the energy for future cataclysms. The state of the core directly controls the planet's thermal evolution, the billion-year timeline of how it has cooled since its formation. This, in turn, dictates the tempo of its volcanism and the stability of its stagnant lid of crust. Did a cooling, solidifying core trigger the last global resurfacing event by changing the way heat escaped? The silent void where a magnetic field should be is a profound clue in this deepest of mysteries, a whisper about the temperature and motion at the center of a world. To truly know Venus, we must listen to its heart, and right now we are still learning the language. The silent heart of Venus holds the key to its future, a destiny written in heat and atmospheric chemistry. So where does this world go from here? Is it locked forever in its current, scorching state, or is it slowly, imperceptibly evolving toward something new? The long-term fate of our sister planet is perhaps the greatest mystery of all, because it asks us to project billions of years forward to see the final chapter of a story we have only just begun to read. One potential future involves a slow, relentless stripping away. Without a magnetic field to protect it, Venus's thick atmosphere remains vulnerable to the constant sandblasting of the solar wind. Over eons, this process could continue to erode the gaseous envelope, molecule by molecule, thinning it out. If volcanic activity were to cease completely, cutting off the supply of new gases from the interior, this erosion might one day win. The atmosphere could thin enough for the crushing surface pressure to drop, and for the runaway greenhouse to weaken, allowing the planet to slowly cool. But this is a timeline of staggering length, and it is not a given. The planet might be in a grim equilibrium. Current volcanic outgassing, even if sporadic, could be replenishing the atmosphere at roughly the same rate the solar wind strips it away, maintaining the status quo. It is a hellish balance, but a balance nonetheless. Another possibility is more dramatic. If the heat building beneath Venus's single plate of crust reaches another breaking point, the planet could experience a new episode of global or regional resurfacing. A fresh wave of volcanism would pump enormous quantities of greenhouse gases back into the atmosphere, reinforcing the furnace and resetting the climatic clock for another few 100 million years. Venus may be cyclical, alternating between long periods of stagnant, oppressive heat and shorter, catastrophic bursts of renewal by fire. Studying this evolution is not just about one world. Venus is the ultimate control experiment for understanding the climate destiny of rocky planets. It sits just inside the inner edge of our Sun's habitable zone, a warning of what can happen when a world tips over the climatic edge. As we discover thousands of exoplanets orbiting other stars, many of them Earth-sized worlds in similar close-in orbits, Venus becomes our essential reference point. It shows us that a planet's location is only the beginning of the story. Atmospheric composition, volcanic history, the presence of water, and even the existence of a magnetic field all weave together to determine whether a world becomes a temperate garden or a scorching wasteland. To unravel Venus's own future, we must go back. Upcoming missions are designed to be time machines. By mapping surface composition with VERITAS, we will see how recently volcanoes have erupted and what they are made of, gauging the planet's internal fire. By plunging through the atmosphere with DAVINCI, we will measure the delicate balance of gases, searching for clues of ongoing change. These probes will listen for the planet's pulse, trying to determine if its heart is cooling towards silence or if it still beats with the heat for another cataclysm. The ultimate mystery of Venus is not just what it is, but what it is becoming. It is a world suspended between a catastrophic past and an uncertain future, a mirror that shows us not only where we came from, but one possible path that lies ahead for any rocky world that wanders too close to its sun's embrace. So the journey through these 25 mysteries leaves us with a profound truth. Venus, hanging in our sky as the morning and evening star, is not a simple cautionary tale. It is a living textbook of planetary extremes, a world where every answer reveals a deeper, more tantalizing question. From its runaway greenhouse furnace to the possibility of metallic snow on its peaks, from the ghostly ashen light to the churning double vortices at its poles, each puzzle forces us to rethink the fundamental rules of how rocky worlds are born, evolve, and sometimes die. The story of Venus is not just about a planet, it is about the fragility of climate, the violence of planetary youth, and the sheer, stubborn ingenuity of nature in the most hostile corners of the cosmos. These mysteries matter because they are not isolated to that one world. They are universal lessons written in acid clouds and scorched rock. Understanding why Venus lacks a magnetic field teaches us about the hidden hearts of planets. Deciphering its lost oceans holds a mirror to our own world's climate future. The search for phosphine, however uncertain, pushes the very boundaries of where we imagine life could exist. Every strange radar echo, every transient hotspot, is a piece of a grander puzzle about our place in the universe. The next great chapter in this story is already being written, not by theorists but by engineers and explorers. Missions like DAVINCI, VERITS, and the European Space Agency's Envision are our keys to the locked box. They will descend through the haze, map the hidden surface in stunning detail, and listen for the heartbeat of volcanic activity. They are our chance to turn these 25 mysteries into 25 discoveries, to replace speculation with knowledge. As we wait for those new eyes to open on our sister world, the conversation continues right here. Which of these Venusian enigmas captivates you the most? Is it the lost oceans, the super-rotating winds, or the haunting possibility of life in the clouds? Share your thoughts below, and let's keep wondering together at the mysteries waiting next door.